Hi there and welcome back to the channel. In this journey, the concept of calculus of variation will be introduced by deriving the Euler-Lagrange equation. Let us start it. Calculus of variations extends the principles of traditional calculus by focusing on optimizing functionals involving functions themselves rather than variables. This branch of mathematics becomes particularly powerful in fields such as optimal control systems. The Euler-Lagrange equation, a cornerstone of calculus of variations, plays a pivotal role in these systems by deriving conditions for the extremal paths that optimize functionals. By utilizing this equation, engineers and researchers can derive optimal control laws, enabling the design of efficient control systems that balance objectives and system dynamics across various domains, including aerospace, robotics, economics, and more. Traditional calculus primarily deals with functions of one or more variables. The function accepts real numbers and maps them to real number as well. Calculus of variations, on the other hand, is a branch of mathematics that deals with studying functionals, which are functions of functions. This means that the input to the function is also a function rather than just variables. Calculus of variations involve optimizing functionals, typically integrals, where the goal is to find the function that either maximizes or minimizes the integral's value. One notable difference between traditional calculus and calculus of variations is that in traditional calculus, derivatives deal with small changes in variables, whereas in calculus of variations, variations or changes occur in entire functions. Let us consider a simple example to illustrate the difference. Traditional calculus deals with functions of variables. For instance, consider the function f of x equal to x squared. To find the minimum value of this function, traditional calculus involves taking its derivative, setting it to 0, and solving for x. Here, the focus is on finding the values of x that minimize the function f of x. In calculus of variations, consider the following functional j of y where y itself is a function of x and derivative of y with respect to x. The goal is to find the function y of x that minimizes this integral. Here, instead of dealing with a fixed number of variables, the goal is to find the function y of x that minimizes or maximizes the functional j of y. In essence, while traditional calculus deals with functions of variables and their derivatives, calculus of variations extends to functions of functions, aiming to optimize integrals involving these functions. These differences showcase how calculus of variations delves into optimizing functionals rather than functions, providing a powerful framework for solving problems that involve optimizing quantities defined in terms of functions, leading to solutions involving entire functions rather than specific values. One application of calculus of variations is optimal control systems, where the equation of Euler-Lagrange plays a big role. Let us drive this interesting equation. Suppose we have a function f of x. This function has two ends at x1 and x2. Also suppose that, for some reason, this function is stretched out and closer function f of x hat is resulted. In different words, f of x hat is f of x plus m, which is a constant multiplied by the function delta of x. It is obvious that f of x approaches f of x hat once m is approaching 0. As can be seen from the figure, both functions f of x and f of x hat have same ends. This means that the delta function is 0 at x1 and x2, i.e., there is no variation at the boundaries. Let us suppose that f of x is unknown and we want to determine this function such that it connects both ends x1 and x2. So, let this function be given as r. The function r is function of our desired function f of x. Thus, we can say that r is a function of the function f of x rather than the variable x. On the right side of the r function, we have the variable x, the function f of x, along with the derivative of f of x with respect to x. Any other required information is also appended in these three quantities. Now let us substitute the function f of x hat into our function. One note to be stated here is that the derivative of the function f of x hat is given as. To minimize the difference between f of x and f of x hat, we need to differentiate the function r with respect to m and then equal the result to 0. This is basically what we would do if we want to find the extreme points of a function with variables in basic calculus. Thus we can write the following, or the following. What we want now is to transfer the derivative with respect to m into the integral. For this, we can use the Leibniz rule. This rule states that as long as the integral bounds are not function of the variable m, we can transfer the derivative outside the integral into a partial derivative inside the integral. Thus, we can write the following. Now let us manipulate the integrand that is highlighted in brown. To differentiate the function L with respect to the variable m, we need to use the chain rule for partial derivatives. Suppose we have a function z that is a function of variables x and y. At same time, both variables x and y themselves are functions of another variable s. Then the derivative of z with respect to s is given by the chain rule as delta z with respect to delta s is equal to delta z with respect to delta x multiplied by delta x with respect to delta s. This is summed up with same differentiation operations for the variable y. After applying the chain rule on our function, we can have the following expression. Keep in mind that we have applied the chain rule on both f of x hat and its derivative with respect to x, as they both are functions of m, whereas the variable x is independent of the variable m. For the new resulted expression, we need to simplify the terms further. The term delta f hat with respect to delta m, as we have from the function f hat, highlighted in blue, is just delta of x. On the other hand, from the derivative of the function f of x hat, we also have delta f hat with respect to delta m is just the derivative delta of x with respect to x. In the newer expression, we can further simplify the second term of the integrand that is highlighted in red. In integration by part, we have the following rule. So, if we choose delta L with respect to delta f of x hat to be u and delta of x hat to be dv over dx, then we can write du over dx as, whereas v is simply the delta of x. Thus the second term of the integrand, according to u dv rule, can be written as, for the first term after the equal sign, highlighted in blue, if we use our boundary conditions, also highlighted in blue, we can assign the term to 0. Consequently, after substituting the remaining terms of the u dv integration into the original problem, we will be left with the following expression. Taking the delta function outside the bracket, the final expression is simplified even further as shown. In the final form of our problem, we need to decide which term is equal to 0 in order for the equation to be satisfied on both sides. As we cannot set the delta function to zeros, otherwise we do not even have an optimization problem here. Therefore, the only term that can be set to 0 is the integrand itself. This is called the Euler-Lagrange equation. The Euler-Lagrange equation in optimal control is pivotal for finding control inputs that minimize/maximize a system's performance criterion. It's utilized to derive the optimal trajectory by solving for extremum conditions within a cost functional. This equation's application spans aerospace engineering, robotics, economics, and various fields, enabling the determination of optimal control strategies to achieve specific objectives under system constraints. Its mathematical framework empowers efficient solutions for real-world problems, guiding decision-making in trajectory optimization, motion planning, and resource allocation. In the upcoming videos, I will illustrate some examples in optimal control employing calculus of variation and Euler-Lagrange equation. As usual, please like the video and subscribe to the channel. See you soon. Hopefully.